In this video, we're going to talk about molecular structures, from the way that they look to the way that they come together to the way that covalent compounds actually act. And everything, again, is dictated by the sharing of those valence electrons. When we share valence electrons, we cause repulsion. Repulsion causes the electrons to move around in a different way. There's only so much flexibility, however, with that movement, which therefore leads to the shapes that we're going to talk about. First thing we're going to look at is a structural formula. A structural formula is not the actual image of what a molecule looks like. Rather, a structural formula will use letters and symbols to show bonds. For example, methane is CH4. This simple diagram is what we would consider a structural formula. Resonance occurs when more than one Lewis structure is valid for any particular substance. So one or more, rather more than one, structure possible. And we'll show an example of this in just a moment. Ultimately, what ends up happening with these resonance structures is that if more than one thing is available and can work, they actually both do work at the same time. And they will simultaneously flip back and forth between the different shapes or the different resonance structures. To show that, we use a double dotted line. And I will show that on the next slide. The picture over here at the right side is a picture of 6 different resonance structures for the formula SO4 with a -2 charge, sulfate. I'm going to show you a slightly easier version, that of nitrate. So we're going to follow the rules for establishing our Lewis dot structure. First and foremost, nitrogen is furthest left on the periodic table, therefore it is your central atom. You'll then add up the different components, or the different valence electrons, and find that 5 plus 3 times 6, 18, gives you 23. But we can't forget right here about this charge. A -1 charge means that there's an extra electron. So because we have that extra electron, we get a total of 24 valence electrons, divided by 2 for a total of 12. Now, to show that this entire thing was given an extra 1 electron, we're going to put the whole thing in brackets and put a -1. That's not the focus of the resonance structure, but it's something we need to learn nonetheless. One of those 12 pairs then gets placed between the central atom and each of the bonding or terminal atoms. Subtract that from the total, you get 9. Then we will satisfy the octet of each of the terminal atoms by placing pairs around. That's 2, 3, 4, 5, 6, 7, 8, and 9. Those dots are really supposed to be inside, but I drew my bracket a little bit close. Now here's the issue. The next rule says place all remaining pairs on the central atom, but we don't have any remaining lone pairs. And so if necessary, we must pull in from the terminal atom to make a double or triple bond. Well, in this case, we only need one more pair of electrons. But what's to say that it comes from this oxygen, or this oxygen? Because all of them are the exact same element, oxygen, and no one is less likely to give theirs, all of them will in fact at one point or another donate one valence electron pair. So this pair will occasionally go into here and make a double bond. That will also happen with each of these pairs here. So at any instant in time, what you will always see is you will see oxygen double bonded to nitrogen, single bonded to oxygen, single bonded to oxygen. So it could look like that, or it could be the double bond has moved over to here, or the double bond's moved over here. The point of emphasis is this: you'll always have one double bond and 2 single bonds with this particular example. So instead of drawing three pictures, what we can do is we can actually simplify the whole matter by drawing one picture. One single bond is always present between oxygen and the central atom nitrogen. To show that a double bond will exist at any of the three spots at one time, we will draw a dotted line symbolizing that. And the final thing we need to denote that this is a polyatomic ion with an overall charge of -1 is to write it in. We'll practice this plenty more in class. With the octet rule, there are a few exceptions, and those exceptions apply to the central atom. Whenever you have an odd number of valence electrons, you're going to have an exception, because you're not working in pairs then. This doesn't come along too often, but occasionally it does. The exceptions that I'm more focused on you learning are the suboctet, meaning we're going to have less than 8 valence electrons, and that's pretty much going to be dependent on the central atom of boron, and the expanded octet, where we have greater than 8 on our central atom. Now specifically we're talking about sulfur or phosphorus for these ones here. This slide here, I'm going to give you an example of just how that would look. Phosphorus pentachloride is a covalent compound that does form. So we have 5 chlorine atoms surrounding our central atom of phosphorus. When we go through the process of adding them up, we get 5 for phosphorus and then 7 times 5, or 35, for chlorine. That gives us 40 electrons to work with, or 20 pairs. To place our initial pairs, we go between the central atom and each of the terminal atoms. Well, now you can already see the problem that's developing. Take that 5, we're left with 15. Following the same rules, we'll then place our pairs around our terminal atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We've used up all our pairs and all of our terminal atoms are satisfied. But the issue lies in the fact that if you look at our central atom here, we have an expanded octet. We don't have 8, we have 10. This is a stable structure for phosphorus and for sulfur, so it's an exception that we do need to take note of. The final talking point that we're going to get to here, and one in which we're going to do much more research, is this idea behind Vesper. Vesper stands for valence shell electron pair repulsion. The idea behind this is that electrons all have a negative charge, and pairs can only get so close to one another before they start to repel away from each other. And so the major idea is that these molecules, depending on how they're bonded, determined by the number of terminal atoms and the number of lone pairs of atoms on the central atom, will basically push away from each other to the point where they can't push any further away because they're getting closer to another pair of electrons. This dictates the shape of the molecule. This chart right here shows you the different shapes necessary. Sometimes it might be easier if you denote this as we have 2 substituents, 3, 4, 5, and 6. Now what I mean by that is we have 2 things on the first line, here and here, to the central atom. Now the second line here, the line of 3, on the first picture we have 1, 2, 3 atoms bonded to the central atom. Sometimes, however, we can have 2, 1, 2 in a lone pair. The lone pair takes up a different amount of space than a terminal atom. Therefore, the shape is different. On line 4 here, we're talking about, okay, in this case, the first one, we're talking about 1, 2, 3, 4 bonded atoms with 0 lone pairs. The next picture, however, still has 4 substituents, where we're dealing with 1, 2, 3 bonded atoms and 1 lone pair. Whereas the picture next to that, the picture right here, features 1, 2 bonded atoms and 1, 2 lone pairs. So you can see here in this diagram that there's a different number of bonded parts, whether they be lone pairs or terminal atoms. And the configuration of this is what determines the shape. And here's just another diagram of that shape. It would be a good idea to get these recorded in terms of the number of lone pairs compared to the steric number or the number of constituent parts.